Team 6. My name is Ahmed. And my teammates Fahim, Muhammad, Zaib, and Alec are working on the analysis and redesign of a clothing iron. And this is our interim presentation. A clothing iron utilizes electricity to heat a metal heating element, which in turn transfers heat to a non-stick sole plate. The sole plate evenly distributes the heat across the fabric, effectively removing wrinkles and creases, thereby maintaining clothing appearance. Currently, our annual demand of iron in the US market is 14.1 million every year. We are targeting 5% of that market, which gives us a production volume of 700,000 irons annually. Our primary customers are the domestic households. We will be focusing 80% of our market on them. The secondary customers will be the clothing manufacturers and the tailors, who will be provided with a gravity-fed dry steam iron. This is our assembly CAD drawing. It shows all the parts in their assembled position. This is the exploded view. We have 16 unique components in this iron. Among them, the plunger and the steam regulator are sub-assemblies that are counting as one part. Each part has a quantity of 1 except for the push buttons.
Our functional analysis found our primary task function is to remove wrinkles. This task function is performed by the basic function of pressing clothes by adding heat and evenly distributing weight. Our second basic function is to allow maneuverability by translation and rotation. For safety, we assure dependability by functions designed to prevent burns that remove energy and control heat. For product convenience and comfort, we prevent water leaks and indicate overheating along with providing steam. We enhance our product above customer expectation by regulating water through the solenoid valve. Our functional component mapping matrix shows us the basic functions of all components. As you can see, we have multiple components that only perform one function. We will try to improve the design by combining some of these parts to reduce total part count and costs. Some components, such as electronics and solenoid valve, are components we can't change or improve, as those are out of scope for this project.
We will now go over 2 possible assembly sequences for this iron. The first sequence is a straightforward, from the ground up process, beginning with the sole plate. In the second assembly sequence, we start with the heating housing, then assemble parts and sub-assemblies, first from above and then from below. Comparing these 2 processes, sequence 1 scores higher in the ease of handling and rotating parts due to a streamlined assembly process, while sequence 2 scores higher in the ease of testing sub-assemblies and parallel assembly due to its major sub-assemblies. Overall, sequence 1 receives 11 points, while sequence 2 receives 9 points.
Here we have our bill of materials. Part costs were determined based on an estimated production volume of 700,000 parts per year. Assembly will be done manually, and we assume that workers would be paid an hourly wage of $16 per hour. A vast majority of our parts use injection molding as their manufacturing process. This is because a lot of parts are thin ABS plastic with intricate geometry. We assumed each mold would cost $10,000. The sole plate and the bracket to hold the solenoid valve are both metal and require CNC milling. We used a quad chart to classify the components based on their functional importance and their manufacturing and assembly cost. The sole plate is expensive to manufacture, but also has high functional importance. Therefore, we will try to reduce the cost, but cannot remove it from the assembly. All other components are relatively inexpensive. The inexpensive parts that have high functional importance will remain the same, but the parts that have low functionality will potentially be changed. This means attempting to combine several parts into one or removing them from the assembly entirely.
Our product family has 2 variants. The majority of our functions are consistent to both customer groups. We differentiate our product by adding additional functions for our secondary customers and industry for how the iron stores, supplies, and regulates the water. We changed 4 parts for the secondary variant. They are the plunger, push button, water lid, and top handle. There's no need for a water lid as the water is supplied from outside. The plunger and the push buttons are replaced with a solenoid valve to accurately send the water. The top handle is changed to fill in any unnecessary cavities. The connection point of the top handle is a snap fit, an alignment feature, and a fastener connection. Even though the top part is changed, its connection feature has not. The solenoid bracket also uses 2 alignment feature and a fastener to securely connect. The bracket will also align with the previous plunger holes that are used for wire and water pipes.
Creating a family assembly plan using the original assembly sequence discussed above will require early differentiation starting after the temperature regulator, because our primary product requires the plunger while the secondary product does not. Therefore, we have designed a more efficient assembly sequence for both of our product variants. All of the parts making up the base of the iron are common between both variants, so they are assembled first. In this case, differentiation occurs after adding the back cover. The primary variant provides the plunger and top cover with 6 other associated parts. The second variant requires the solenoid mechanism valve and the modified top cover without openings. So that concludes our thesis in presentation. Thank you for listening.